Hi everybody. In this section we're going to use what we know about functions that we've established so far and build the idea of an exponential function. The timing of this couldn't be better. It's really too bad that we can't be together in class to talk about how these exponential functions pertain to our current situation with coronavirus. The whole reason that we're all at home is because coronavirus is spreading at an exponential rate, and in this lesson we're going to explore exactly what that means. I'm going to include a number of videos along with the one that I'm posting here related to coronavirus. Make sure that you watch those to kind of give some perspective to how what we're doing relates to the world at large. So 3 things we want to accomplish. We want to define what an exponential function is. We want to be able to graph exponential functions. And then we're going to look at some applications involving these types of functions. So let's get started. Okay, for starters, consider this situation. Suppose you have somebody who decides that they're going to come up with a little money-making scheme here. They're going to write what's called a chain letter. Here's how it's going to work. This one guy gets the idea that he's going to send a letter asking for money to each of his 5 friends. Now let's keep track of how many weeks have passed, assuming that it takes him a week to send the letters, and how many new letters there are at each week. When no time has passed, the only new letter is the one that he's written. He hasn't done anything with it. Now, when he sends this letter asking for money to each of his 5 friends, they all are probably kind of put off because they've gotten this letter asking for money. But let's note that 1 week has passed, his 5 friends have gotten their letters, and that could be the end of it. But here's the kicker. The letter that he sent out encourages each of his 5 friends to forward the letter to 5 more friends and do the same thing. Now, if his friends agree to this, and we'll assume that they do, then they all send a copy of the letter to 5 more people. If that happens in the 2nd week of this process, then how many people would get that new letter? Each of these 5 people is sending out their own 5 copies, so we have 5 new recipients for each of those original 5. We would now have 25 new letters. Now, of course, what are those 25 new recipients going to do? They're going to follow the instructions in the letter, and they're going to send out a copy to their 5 best friends. Now, this gets to be a little bit difficult to draw, but hopefully you can start to observe a pattern here. If we let another week of this process pass, and every one of these people sends it out to 5 more people, then how many new recipients would there be? We started out with 1, and that went to 5 people, which gave us 5 after week 1. And then they all sent it to 5 people, and that gave us 25. Now they're all going to send it to 5 new people, and we'll have 125 recipients. What about after week 4? They'd all send it to 5 new recipients, and we'd have 625 recipients already. And you can see this is starting to get out of hand. Now I want you to take your calculator and look what happens with 2 more weeks. After week 5, we'll have 3,125 new letters. And after week 6, there will be 15,625 new letters. That rapid spreading of this letter is a perfect example of what exponential growth looks like. Now, what's the equation that relates the number of weeks that's passed to the number of new recipients? Well, the number of new letters, and we'll write this as a function, so the number of new letters depends on the number of weeks that has passed. And so we'll let the number of weeks that have passed, we'll let that be x. So the number of n for new letters is the result of multiplying by 5 every week, or in other words, every week that passes, we multiply it by 5 again. So if you look at our numbers, you'll notice that each one of these values is a power of 5. 5 is 5 to the first power. 25 is 5 to the second. 125 is 5 to the third. 625, that's 5 to the fourth, and so on. And even way up here at number 1, 1 is equal to 5 to the 0 power. So what you should observe is the exponent on the number of new letters is the same as the week that we are keeping track of. Second week, 5 to the second, or 25 letters. Fourth week, 5 to the fourth, or 625 letters. So we can say that the number of new letters is always equal to 5 to the x power. So as long as your calculator is out, how many new letter recipients would there be at 10 weeks? The number of new letters after 10 weeks, we'll plug 10 into our function. That's going to be equal to 5 to the 10th power. Type that into your calculator. Make sure you can find your exponent button. We've used that already in this class. You should know how to enter that. And you will get 9,765,625 new letters, which is pretty remarkable. Now let's graph that. So we've written a function that describes this. We said the number of new recipients based on the number of weeks that passed x will be 5 to the x. If we graph that, when 0 weeks had passed, there was only one new letter, and it was one that our original author had written. But then after 1 week had passed, 5 new letters got sent out. After 2 weeks, we were already up to 25. So you can see that this is not increasing linearly. This really takes off steeply, and that's what exponential functions do. And this is exactly why we're all staying home right now. If each person who has coronavirus infects 3 other people in casual contact, you can see what will happen to the number of people who get the virus. And for folks that do need to be hospitalized, that puts a lot of pressure on the healthcare system in a real big hurry. Now, what would this curve look like if the person who wrote the letter would have only sent it to 2 other people instead of 5? He'd still start out with 1 letter, but after 1 week, only 2 new people would have it. After 2 weeks, we'd only be at 4, and after 3 weeks, we'd only be at 8. So we'd still be growing exponentially, but it wouldn't be climbing as fast. That's what we're doing with social distancing. Instead of the typical person infecting 3 or 4 new people, we can maybe reduce that. So the typical person who has it only infects 1 or 1.5 or 2 people, and then we can slow down the spread. Now, not all exponential functions grow. Some decrease, or what we say is decay. So let me have you think about this situation for a minute. Suppose there's a fresh pan of brownies in your kitchen, and you walk up to the pan of brownies, and if you like brownies as much as I do, you decide that you should probably not eat the whole pan. So you make a rule, and you say, look, every day, I'm only going to eat half the brownies in that pan. So on day 0, when the brownies are fresh, there is 1 whole pan of brownies. Now, when you go back the first day, you go find that full pan of brownies, and you allow yourself to eat half of it. So after 1 day, the number of brownies that are left in the pan drops to just a half. Now, when you go back the second day, there's only half a pan there, and if you eat half of that, then only 1/4 of the brownies are going to be left. So then if you go back on the third day and allow yourself to eat half of what's left, how many brownies will be left? Well, at that point, it'll be about 1/8. And the day after that, it'll be a 16th, and the day after that, a 32nd, and so on. Will you ever run out of brownies? No, you won't. And this is an example of exponential decay. It's decreasing and it's decreasing, and it doesn't decrease as much as it did the day before, but it's always fading away. But it never quite touches 0 either. Now, these concepts are what we want to build on in this topic, the idea of exponential growth and decay. So let's keep going. All right, so more simply, let's look at these 2 cases. Let's consider a function where we have 2 raised to the x power, and let's graph that. And we're going to graph the function g, which is 1/2 raised to the x power. And understanding the difference between these 2 results will be the key to what we're going to do. Let's start with our first graph. Let's make a table. So let's pick some values. When x is equal to 0, this becomes 2 to the 0 power, which is 1. And so that means 0, 1 is a point on our graph. When x is equal to 1, we have 2 to the first power, which is 2, and so 1, 2 is on our graph. When x is equal to 2, we have 2 to the second power, which is 4. When x equals 3, we have 2 to the third power, which is 2 times 2 times 2, or 8. And when x is equal to 4, we have 2 to the fourth power. 2 times 2 times 2 times 2 is 16. And you can see that already we've reached the top of our graph. So what we have here is another example of exponential growth. But we can also plug in negative numbers into this function. For example, when x is equal to -1, this becomes 2 to the -1 power. Now we know negative exponent means reciprocal, and that is 1 over 2, or in other words, 1/2. So at -1, we have a y value of 1/2. Let's use one more point. -2, that's 2 to the -2nd power, which is 1 over 2 to the 2nd power, or 1/4. So 2 to the left, we're down at 1/4. And so this exponential growth, as we go off to the left, actually drops down and gets very, very close to 0, but runs right alongside the axis. Now, as you can see, as we move from left to right, this function is growing. This is exponential growth. Now, the thing that makes this thing grow, and the biggest factor in its shape, is what the base is. We said this was for a function, f of x is equal to 2 to the x. That number is called the base of our function. Or sometimes we call that the growth factor. And as you can see, every time we move to the right, 1, 2, 4, 8, this went up by a factor of 2. Now let's graph this other function, g of x equals 1/2 to the x. Let's have a growth factor of 1/2, or a base of 1/2, and see what that looks like. Okay, exact same idea. Let's make a table of values. When x is 0, we have 1/2 to the 0th power. Anything to the 0th power is 1. When x is 1, we have 1/2 to the first power. That's 1/2. And when x equals 2, we have 1/2 squared, which is 1/4. So we can plot 1, 1/2, and 2, 1/4. Now, as you can see, this is dropping down. We started out at 1, and we're dropping down as we move to the right. The next value would be 1/8, 1/16, 1/32, and so on, but it'll never quite reach 0. Let's plug in some negative numbers. When x is equal to -1, we have 1/2 to the -1 power. That's the same as, since negative exponent means reciprocal, 2 over 1 to the +1 power, which is 2. When x is -2, we have 1/2 to the -2nd power. That's the same as 2 over 1 to the +2nd power. Again, negative exponent means reciprocal, and that's equal to 4. And hopefully that's enough for you to see what's happening here. This is the mirror image of our exponential growth function. This is exponential decay. This function was given by g of x equals 1/2 to the x. And so because our growth factor was small, was less than 1, it actually decreased as we moved to the right instead of increasing. Now let's summarize what we've done so far. In general, growth functions look like the example on our bottom left, and decay functions look like those on the bottom right. That's what we just saw. Notice that they both passed through the point 0, 1. Anytime we have a base that is bigger than 1, like we had in our exponential growth model where our base was 2, then this function increases. But when the base is less than 1, now it still has to be bigger than 0, but when our base is between 0 and 1, we have exponential decay. A couple things to note about this graph. First of all, we can generalize this and say any exponential function, this is very important, any exponential function has to have the form ab to the x power. Now, because we were looking at simple cases, we let a be 1 so that we could pretend it wasn't even there. But if there's a coefficient, that takes the place of a. b is the base of our exponential function, and that always has to be a positive number. That is to say, it has to be bigger than 0, but the base can't be 1 either, otherwise the function stays flat. And a is our starting value if we're starting at something other than 1, and we'll talk more about that in a little bit. A couple things to note about these graphs. The domain of these graphs is negative infinity to infinity. That was true for the exponential growth function we looked at a minute ago. The domain reached forever to the left and right. And the same thing was true here. The domain reached forever to the right and forever to the left. In other words, we can plug any number we want into that exponent. Anything positive, anything negative, or even 0. The range of these types of graphs is from 0 to infinity, not including 0. Note there's a parenthesis there. And again, that was true for our graph here. The range only went down to 0, so we would have a parenthesis on that end, but the range went up forever. The graph increased without bound. And the same thing was true with our exponential decay model. The range only reached down to 0, but it reached up to infinity. If there's an a value on this function, which our first two examples didn't, but if there's an a value in front, then that tells us what our y-intercept is going to be. It's going to be at 0, comma, a. We'll see that in just a minute. The line y equals 0, that is to say the x-axis, that is an asymptote of the graph. Exponential growth and decay both want to hug that line as they go off to the extreme left or right values, but they'll never actually reach 0. But here's the most important thing. As I said before, when our base is bigger than 1, we get exponential growth. But when our base is less than 1 and still positive, that is between 0 and 1, then we get exponential decay. Okay, let's take a look at a couple more examples here. Okay, let's look at a couple of graphs. Let's graph f of x is equal to 3 to the x. Now, we don't need to make a table of values here. Think about this for a minute. F of x is equal to 3 to the x power. Now, is there a number out in front of that? Sure there is. We can say that there's a 1 in front of that. So this is of the form ab to the x power, just like the functions we just looked at, where a is equal to 1 and b is equal to 3. So since our a value is 1, that means our graph is going to start with a y-intercept of 0, 1. And since our base is 3, that just means we're going to increase by a factor of 3 every time we move to the right. So when we move to the right 1 times 3 is 3. When we move to the right again, multiply 3 by 3, and we get 9. 9 times 3, that would put us way up at 27. That's going to be way up here, and there's our exponential growth. As we move to the left, that would drop by a factor of 3. Our next point to the left would be 1/3, and then 1/9, 1/27, getting smaller and smaller, but never actually reaching 0. And so there's the graph of f of x. Now that's steeper than our original one, but that's because our growth factor was a little bit higher. Okay, what about our second function? G of x equals 1/4 to the x. Okay, that's just like saying 1 times 1/4 to the x, and therefore our a value is 1 and our b value is 1/4. So we're going to cross at a y-intercept of 1. Since b is 1/4, that means we're going to change by a factor of 1/4 as we move to the right. 1 times 1/4 is 1/4, times 1/4 is 1/16, and that one drops really, really fast. As we go to the left, that means it would go up by a factor of 4, because we'd have to be at 4 if moving to the right drops us down to 1. Before that, we must have been at 16, because 16 times 1/4 means that we would drop to 4. 4 times 1/4 means we would drop to 1. And if you're not so sure of that, just plug in the number. Let's find out what the value of function g is at -2. G of -2 is 1/4 to the -2nd power. That is 4 over 1 to the +2nd power, which is 16. And that's where we plotted our point. Now let's look at some transformations. Let's look at h of x. H of x is equal to 3 times 1/4 to the x. Now this is just like the one we just did, but notice here our a value is 3 while our b value is 1/4. That changes things. When our a value is 3, that means that we would start out with a y-intercept at 0, 3. When we move one spot to the right, 3 times 1/4 would put us at 3/4. And if we move to the right again, we'd be at x equals 2. Let's check that out. H of 2 is equal to 3 times 1/4 squared. That is 3/16. And so this second function drops almost as much, but it stays slightly above. What about x of -1? H of -1 is equal to 3 times 1/4 to the -1 power, or in other words, 3 times 4 over 1, which is equal to 12. And so when our x value is -1, our y value is 12. So our h of x is just the same as our g of x, except that factor of 3 means it's going to be 3 times taller at every point. Now, look at our last function, j of x. J of x is just like our original function g of x, but it's had some transformations applied to it. Just the kind of stuff we've done before. First of all, there's an inside transformation right by the x. There's a negative sign in front of the whole thing, and then 1 was subtracted from the end. So we would start with our graph of g of x, which I've kept right here. What would this -2 do? That's an inside transformation just to the x. That moves us to the right 2, which means each one of these points is going to get moved to the right 2. I'm going to draw that with a dashed line. Next, we'd apply this negative sign out in front, and that, of course, flips this function over. And so instead of staying above the x-axis as we move to the right, we're going to be below the x-axis as we move to the right. So there's our function once it's been flipped. And then finally, this -1 on the end is going to make us drop down 1 unit. So if we take all those points and move them down 1 unit, instead of climbing up to the x-axis, we're going to climb up to the line y equals -1. And there's the graph of j of x. That's just like the original graph of g of x, but it's had our 3 typical transformations applied to it. Now, one of the reasons that's important is because it adds 2 new base functions to our family. So let's review what we have so far. They were the function x squared, x cubed, and absolute value of x. You should know what those look like. I'm going to give you a minute to think about each one. Of course, x squared is a basic parabola. X cubed is a zigzag like a twisted parabola. And the absolute value of x is our v function. If those don't come to mind immediately, you need to study those. Then we added 2 more functions when we were working with roots. They were the square root of x and the cube root of x. Do you know what those look like? Hopefully so. The square root of x starts at 0 and moves to the right because we can't take the square root of any negative numbers. The cube root of x has a domain from -infinity to +infinity, looks like this, and we can take the cube root of negative numbers. Those are the original 5 base functions. Now, we're going to add two more. And the two that we're adding now are the exponential growth function ab to the x, both where b is bigger than 1 and where b is between 0 and 1. So what does the exponential function look like with a base that's bigger than 1? Well, it should cross through the point 0a and it should be growing. That gives us an example of exponential growth. And if b is between 0 and 1, we're going to cross through 0a, and that gives us exponential decay. So make sure that you add these to the list of base functions. We now have 7. Okay, the last thing we need to do is take a look at a few applications of exponential functions. So one of the simplest examples is exponential. One of the simplest examples is compound interest, which is exponential growth with money. If you put money into an investment or into an account with a fixed interest rate, it gets paid k times per year. Now that can be twice per year or 4 times per year, or if it's monthly, 12 times per year. And you get an interest rate that is the value of r, then the amount a that you'll have in the account after t years is given by this formula. We know that this is an exponential formula because t, which is what your balance depends on, is up here in the exponent. So the question is, how much will you have in your account at the end of 45 years if you put $3,000 in there now at a rate of 6% compounded quarterly? Okay, well, we can use the formula directly. We're trying to find a, but the question is, what are our parameters? 45 years, well, that's our t value, so t is equal to 45. P is the amount we're depositing, and so apparently P has got to be 3,000. Interest gets paid k times per year. Quarterly, well, there's 4 quarters per year, and so our k value is equal to 4. And our interest rate is 6%, but that needs to be in the form of a decimal, so we're going to call it 0.06. All right, here we go. Then the amount we'll have is 3,000, or our p-value, times 1 plus our interest rate of 0.06 divided by our k-value of 4 raised to the k times t. That's 4 times 45. Okay, stop there for a minute. That's inserting all of our parameters into our formula. And now you should pull out your calculator. So we're going to have 1 plus 0.06 divided by 4 is 0.15. And then our exponent is 4 times 45. That's 180. So going a step further, that's going to be 3,000 times 1.015 to the 180th power. And that's why this is exponential growth. So take just a minute now, and in your calculator, take 1.015 and raise that to the 180th power. And once you get that result, multiply it by 3,000. Make sure you're doing the exponent before multiplication here, though. That's basic order of operations. Okay, you should get $43,753.10. If you're not getting that number on your calculator, pause the video and make sure you get that. There's a number of WebAssign problems that will have you doing that exact type of calculation. Now, before we leave this problem, though, there's one more thing I want to point out. Before you got your number of 43,753, look at what you had to do for a calculation. We had 3,000 times 1.015 to the 180th power. This is exactly like our model for exponential function. We have an a value of 3,000 because that's what we started with. Our b value is 1.105, and our variable, which was time, was part of the exponent. Now that a value of 3,000 means that's what we started with, and we went up from there. our B value of 1.015. Now, that's bigger than 1, of course, so that we know that this money is going to be growing, but it's just barely bigger than 1. So what does that mean if it's just barely bigger than 1? Well, it's going to grow, but it's not going to grow very fast. If you wanted your money to grow faster, we'd have to get a bigger growth factor here. And what is it that determines the growth factor? Yeah, of course, it's that number right there. That's our interest rate. So by finding an investment that pays a higher amount of interest, that increases our growth factor, and then instead of our money growing exponentially like that, we might get it to grow exponentially like that. Population is another great example of something that grows exponentially. So we're going to take a look at two countries here, Canada and Greece. And we want to look at what the population growth for each of these is. If we were in class, we would do a little bit more with this, but given our limitations, we're just going to do a basic calculation so you can do this computation. Canada's population in 2016 was 35,151,000 or so. And so what is the expected population in 2020? That's an easy question to answer if we know the growth rate. Canada's population does not grow very fast. Its growth rate is less than 1%. It's only 0.90%. Now it is positive, which means Canada's population is growing, but not very fast. So let's plug these numbers into our formula. How much time are we going to let pass here? We know what the population is in 2016. We want to know what it is in 2020 or right now. Well, that's a difference of 4 years. And so the population 4 years after we have the initial population in 2016 is equal to our initial population. Anytime we have a subscript on a variable of O, that means the original number. So that's going to be kind of like our investment in the last problem, 35,151,000 times 1 plus our growth rate. Now, we can't use 0.90, that's 0.90%. We have to turn that into a decimal, 2 places to the left. That's 0.0090 when we turn it into a decimal. And then we're going to raise that to our t value, which in this case was 4. So we can combine these values inside the parentheses. That's 35,151,000 times 1.009 to the 4th power. And here again, you can see that exponential growth model, a, b to the x. Our a value is what we're starting at. Our b value is our growth factor. It's a little bit bigger than 1, which means this population is growing a little bit. And you should type that into your calculator. 1.009 to the 4th power times 35,151,000, and you should get 36,433,622 or so people. Now, there's no way we'd be able to get it that precise, but that is the calculated value. If we wanted to round that to the nearest thousand like our initial number was, we could reasonably call that 36,434,000 people. And since this is a census year, these numbers would be updated soon, and so we'd be able to check and see if that prediction is correct. Now I want you to take a minute and do a similar problem. Greece's population in 2017 was 10,768,000. Greece, though, because of a number of factors, including a really unstable economy, has a population growth rate that's negative. It's negative 0.21%, which means what about Greece's population? It's actually decreasing a little bit each year. So you take a minute, pause the video, and figure out what Greece's population is in 2020, or about right now, based on that growth rate from the population in 2017. Unpause when you're ready to see that solution. Okay, first of all, recognize that that growth rate needs to be converted to a decimal. That's negative 0.0021. And now we can substitute those values in. We're also recognizing that from 2017 to 2020, we're only dealing with 3 years here instead of 4. So our population 3 years after the time that we started at will be 10,768,000 times 1 plus, but this is a negative number, so it's going to be 1 minus 0.0021 to the third power. Now, if we take that a little bit further, we can say that that is 10,768,000. 1 minus 0.0021 is 0.9979 raised to the third power. And look at what we've got. There's that exponential form again. Our A value, our starting value, is 10,768,000. Here our B value is a little bit less than 1, so that's an exponential decay. This is dropping very gradually. But if you do that computation on your calculator, you will get 10,700,304 people, which is of course a little bit lower than it was 3 years ago, and that's what you'd expect. Here again, this could be rounded off at 10,700,000.
Okay, let's take a look at one more example here before we wrap this up. Another example of exponential decay is the way that vehicles depreciate over time. When you buy a new vehicle, it depreciates pretty quickly when you drive it off the lot. And it depreciates much faster when it's new than once it gets older. So when you buy a vehicle, of course, we start out at that A value in our A, B to the X model, but then it drops pretty steeply in value, and then it flattens out over time. So it doesn't necessarily reach 0 for a long, long time. It'll always keep some of its value. So we know that A is the initial price of the vehicle, and B tells us how fast the vehicle decays. So I think you would agree this is exponential decay, and therefore our B value has to be between 0 and 1. So let's figure out what those values are for this Toyota Tacoma. Now the Toyota Tacoma is the vehicle I've chosen here because they're known for holding their value really, really well. So it provides a good example for us. Suppose this Toyota Tacoma depreciates at a typical rate of 7% of its value per year, and it's on Craigslist, a 2013 model truck for $24,250. So we know that in general this thing is going to follow the exponential model. We want to find its value when it was new, so we need to find the value of A. Now we know a couple of things. It depreciates at a rate of 7% per year. Now here's the key. Think about Greece's population that we looked at just a minute ago. We subtracted that from 100%. If it loses 7% per year, or in other words 0.7 per year, then our B value must be 100%. That would mean it wasn't losing any value year after year, minus the 7% that it's losing. That means that our B value is 93%. Or another way to say that is it keeps 93% of its value each year. And so if it keeps 93% of its value each year, we can say then that our B value is 0.93. And so our Y value, or our output, is going to be A times 0.93 to the X. Now, our X value is our time. This is a 2013 truck. The year is 2020 right now, and so this truck is 7 years old. And so our time is 7 years. Just like our Greece example, that's going to be our exponent. So in other words, it's kept 93% of its value for the first 7 years of its life. Now we know what it's worth now. We know that it's worth $24,250. That's its current value. And so 24,250 is equal to A times 0.93 to the 7th power. And now we have an equation to solve. 24,250 is A times 0.93 to the 7, so let's divide that off. And that means the A value in this exponential decay problem is 24,250 divided by 0.93 to the 7th power. Make sure you try that in your calculator. You should get $34,643. That was what this started at. So for perspective, that means that when this Toyota Tacoma was new, it was worth $34,643. That's our A value. It's been depreciating for some time. The 34,643 is what it was worth when it was 0 years old. Now that it's 7 years old, we know what it's worth. The value at that point is what it's for sale for right now, $24,250. And that means that we can project what this vehicle will be worth in the future. So our second question is, what will it be worth in 5 years? Well, think about our graph. 5 years from now, the vehicle will be not 7 years old, but 12 years old. And we would like to figure out what its value will be at that time. But here's the key. As long as we know our A value, which we now do, and as long as we know our B value, which we knew right away, if it loses 7% per year, it's keeping 93% of its value, then we can generalize that and say its value will be 34,643, which is our A value, times our B value of 0.93 to our X value, which is the age. And so we're going to let X be equal to 12 years old, which is how old it will be in 5 more years. And so its value will be 34,643 times 0.93 to the 12th power. And again, calculator problem. And you should get $14,501. So 5 more years into the future, this will drop to $14,500 or so. And we've answered that question. Now a quick word about coronavirus. Coronavirus is doing exactly what we're describing here. It started out at one point with one person who was infected. Nobody really knows exactly how that happened. There's a lot of theories, and you can read about those on the internet. But it started out with one person. And of course, the time here we would measure in days as opposed to years or even months. Every day this is changing. But certainly coronavirus is increasing the number of people who are infected exponentially. And so we know that coronavirus has to follow that model. But we know that A was 1. But here's the problem. We know that B is bigger than 1. But what makes this so tricky is nobody really knows what the base is. We don't really know how fast this is spreading. The goal right now is to keep that base as small as possible. And again, that's why we're all separated, because if we can make the growth rate go flatter, then this is a much easier situation to manage than if the base value is very high and it takes off exponentially very, very quickly. And so our goal in the next few weeks is to keep our base value small, to keep this curve from growing fast. Okay, as I said, I'm going to provide some other interesting links that relate to this topic. It's so relevant right now, but that's it for this topic. There's really 2 things that I want to note here in summary. First of all, this covers all of the important information. Exponential functions follow a form ab to the x, where b determines whether this thing is growing or decaying. A is our starting value. If b is bigger than 1, then we have an exponential growth situation like the one on the left. And if b is less than 1 but bigger than 0, then we have exponential decay. And hopefully that's where we'll get with coronavirus at some point, where people have built up an immunity, and then the prevalence of the virus will actually be decreasing. We know that this graph will always hug the x-axis, that is to say y equals 0 is a horizontal asymptote. We always We know it always stays above the axis, and we know that it has a domain of all real numbers. The other thing that I want to make sure that you recognize is important from this topic is that adds two more base functions for us to know. In addition to our first five, which you should be very familiar with at this point, we have exponential growth where b is greater than 1 and exponential decay where b is less than 1. And you should recognize those two curves. We're going to build on those even more in the next few lessons. So that's it for now. Go after the homework and again, reach out if I can help you out.